Hey everyone, and welcome to This Explainer. You know, if you're a college student right now, chances are you've sat through a few, let's say, highly stressful engineering or physics lectures. You know the ones, where the formulas are just flying across the whiteboard and you're frantically trying to keep up while your stress levels literally go through the roof. Well, today, take a deep breath. We're going to do something completely different. We're treating this less like a high-pressure exam prep session and a lot more like a gentle, guided exploration of how energy actually works. We're going to look at the invisible forces that literally light up our lives, and we'll use some very grounded textbook notes and handwritten student guides to make perfect sense of the whole shebang. I want to start by posing a really simple, fundamental question. How do we actually harness invisible energy? Think about it. Just look around you right now. Your laptop, your phone, the lights overhead, maybe that coffee maker humming away in the kitchen. They're all drawing on something we can't even see. It's kind of like magic when you first think about it, right? But it's actually rooted in a deeply structured, truly beautiful set of physics. And to understand the math behind it all, we first need to pause and just appreciate the fundamental nature of the electricity powering our modern world. There is this fantastic line in our source material that just perfectly sets the stage here. The textbook states, quote, "Electric energy does not occur naturally in usable form and must therefore be centrally generated and instantly transported," end quote. I mean, think about the gravity of that for a second. We can't just go out into the woods and mine a bucket of usable electricity. We can't simply scoop it up from a river. We have to carefully, intentionally transform it from other sources, like chemical, solar, or mechanical energy, and then precisely direct it to exactly where it needs to go, exactly when it needs to be there. Okay, let's dive into Section 1, Defining Real Power. Now, I promise we are going to look at this definition entirely without the math anxiety. When we talk about real power in engineering, we're really just talking about the actual tangible work getting done. We're looking at the rate at which this invisible energy is successfully delivered to your device to actually make it function. Electrical power is simply the rate at which work is done or energy is delivered. Mathematically, it's expressed in this really elegant, simple formula: P equals V times I. Power is just the beautiful, harmonious relationship between voltage, which you can think of as the push or the pressure in the system, and current, which is the actual flow of the charge. It's exactly like a water hose in your garden. Voltage is the water pressure forcefully pushing through the rubber, and current is the actual volume of water flowing out the nozzle. When that pressurized flow finally hits a water wheel and turns it, that is when you get real power. To truly ground this concept, it's great to look at how a student actually jotted this down in their notes. There's something just incredibly relatable and human about seeing this written out on a piece of standard notebook paper, isn't there? You see right there in the center, power in electric circuits is obtained as the product of voltage and current, P equals VI. And the unit is the joule per second, or the watt. It's literally just the rate of work. It's a simple, undeniable fact of nature and absolutely nothing to be intimidated by. All right, moving right along to Section 2, the players, active versus passive. Let's see how this builds, because to understand power, we have to understand the different characters interacting within our electrical circuits. I want you to think of a circuit like a tiny self-contained ecosystem. And, in any healthy ecosystem, you naturally have different roles to play. You have the elements providing the vital resources and the elements consuming or utilizing them to survive. In our electrical ecosystem, we have a wonderfully clear, stress-free distinction. On one side, we have active elements. These are the dedicated suppliers. Think of your batteries, your wall outlets, your voltage sources, your current sources. Their entire job is just to give energy to the system. On the exact opposite side, we have passive elements. These are the receivers. They don't generate any energy of their own. They simply react to what they are given. They either gracefully use the energy up, or they hold on to it for a little while until it's needed later. If we look closely at this handwritten classification, we've got three main characters listed under passive elements. We have the resistor, the inductor, and the capacitor. Honestly, no matter how incredibly complex your computer's motherboard might look, these are the three main foundational ways our circuit interacts with the energy that's been supplied to it. Let's quickly break down the peaceful reality of these three components. Resistors gently dissipate energy, usually as heat. Remember when you're studying late at night and you feel that familiar, comforting warmth on your laptop charger? That's just a resistor doing exactly what it's supposed to do. Capacitors, on the other hand, are kind of like little temporary storage tanks. They quietly store energy in electric fields. And inductors do something quite similar, but they store their energy in magnetic fields instead. Every single component knows its role. They either use the energy or they patiently hold on to it. It's just a profoundly balanced system. And that idea of system balance brings us perfectly to Section 3, finding balance through maximum power transfer. Very often in university engineering classes, this topic is taught as a brutal, complex calculation that you just have to memorize to pass a midterm. But I want you to look at it totally differently today. The maximum power transfer theorem is really just about finding a perfect state of harmony. It's about figuring out how to elegantly get the most out of what you're putting in. Looking at the textbook's Thevenin equivalent circuit and the resulting power transfer efficiency equations, the math is telling us something truly profound. It shows us that maximum power is delivered to the load only when the load's resistance perfectly matches the source's internal resistance. It's not about overwhelming the system with raw energy, it's about aligning the two sides so they match perfectly. The actual steps to get there are surprisingly straightforward. First, you represent your entire messy network as a simplified Thevenin equivalent. Basically, you clean up the noise. Second, you carefully adjust your load resistance so it flawlessly matches the source resistance. Think of it exactly like riding a bicycle up a steep hill. If you're in the wrong gear, you pedal furiously, completely exhausting yourself, but you barely move forward. But when you shift into the perfect gear, matching your leg's natural resistance to the steepness of the hill, your energy transfers perfectly into motion. When those match in our circuit, you hit step 3. You achieve maximum power delivery. We call this impedance matching. It is a beautiful, efficient symmetry. As we wrap up our exploration of these foundational concepts, let's move into Section 4, a low-pressure takeaway. I want to transition to a final, incredibly comforting realization about circuit design, energy transfer, and honestly, maybe even a little bit about our own daily lives. If we look closely back at the textbook's mathematical proof, there is a fascinating hidden truth sitting right at the bottom of the page. It calculates the efficiency of power transfer under these maximum conditions we just talked about. When you perfectly match the resistances to pull the absolute maximum possible power out of the source, the efficiency drops to exactly 1/2, 50%. This is such an absolutely crucial point to understand. Maximum output does not mean perfect efficiency. In fact, in physics, it's the exact opposite. When a circuit is running at absolute maximum capacity, when it's pushing as much raw power as it possibly can to the load, you naturally lose exactly half of your source energy to the system as heat. 50% of the energy is completely lost to the surrounding environment just trying to maintain that maximum output. You are literally burning up your reserves just to hit the absolute limit. I think that's an incredibly peaceful, validating takeaway for college students and really for anyone navigating a busy life. In circuits and perhaps in our own minds and bodies, running yourself at absolute maximum capacity means you're going to burn half your energy just as heat, stress, and burnout. Sometimes, intentionally stepping back from maximum output is the only mathematical way to actually run efficiently and sustainably. So it leaves us with a grounding thought to reflect on today. Where else in your life are you sacrificing your own efficiency and peace just to achieve maximum output? Take a breath, find your balance, and I'll see you in the next explainer.